So in the previous class you have seen that we have showed you the machines. We have all the machines here of different technologies, that is FDM based, that is multi-jet printing, carbon fiber one. Now what we will do is that we have told you to give us some chessboard pieces, so we got some. So we took one, we downloaded one, and we will just show you how do we import the files and do all the settings in the software. Fine. So for that we are using this machine, the Stratasys one. So this is the machine we are going to use right now for printing. The problem with other machines is that we have carbon fiber here, and in our course curriculum we have already a separate this lab class for this carbon fiber, right? So we will show this printing later in some other videos. We have already recorded the video, so we will show you how do we do the recording here. Talking about that machine, so we have some problem with the machine, the multi-jet printing. Here what happens is that we already told you in the last video that we have some liquid, we have powder material that is melted and then made in liquid form, and then it basically jets the liquid, that is the part material, and then it prints the thing. So right now we are going to use this machine, fine, that is FDM based machine, that is fused deposition modeling. So we have this software, fine. So this is the GrabCAD software. You can see the name here, GrabCAD print. So if you just type in the Google, you will find it, and from that website you can get some models also, important models for your project work also. So this is the CAD print, fine. So I'll just show you the software. So this is the software which we are going to use, GrabCAD print, fine. So this is the part, this is the interface we have here, fine. So this is the part where we can see the print. Here we have one more part where we can see the scheduled work. So for example, if we have many models that is prepared, so we will have the queue here, number of parts. Right now we don't have any queue, we don't have any parts, and here we can see the array. So basically now the printer is not connected with the computer via LAN. So we have one facility that we can connect the computer with the machine via LAN. So once we connect, we can see the printing history here, fine. So for how many hours we have operated the machine, what is the present condition of the machine, what is the temperature, and many things like what is the material, how much amount of material we have here, everything we can view here. So this is the printing history, fine. So if we don't have this option because the LAN is not connected properly, fine. So this is the basic interface, fine. Now we will go for the import of the material, fine, import of the model, fine. So let me open this one. So we have this one chess piece, fine. So let me just open it. So we have this one, this is the model we can see, fine. So we'll just zoom it, fine. So you can see this is the model we have here, fine. You can see, fine. And we have here some of the views we have here, fine. So this is the top view we have, fine, top view. We have this bottom view, we have this left view, we have this right view, we have this front view and back view, fine. This is the isometric view we have here, fine. So you can see all those settings we have here, fine. So via this we can view the model in different angles, fine. And here we have some of the parts, fine. So what we will do is that first of all we will go for material. If there is any error in the material, so we'll just click here, fine. So we can see there are no errors in the material model, fine, everything is okay. If there are some errors, we can obviously repair it. So we have this option, that is repair all models, fine, and we can view this number of errors we can have. So 3 major errors we can have in this model, that is self intersection, open faces and inverted normals. So all those things are covered in the first video, fine. This is the option where we can see the slice preview. Now slice preview is something where we can view the number of slices or number of parts the machine will print, like in layer wise manner, fine. So I'll just show you what is the meaning of slicing, what we can view in the slicing part. So see, this is the part we have here, fine. So in real-time condition, how the part will look in the 151th layer. So this is the layer we have here, 151 151th layer, and in 151th layer this type of thing we can view, fine. So the orange color portion is the support material. This is the orange color portion, that is the support material, and the green color is the model material. So you can see here, this is the display portion. The model material is indicated in green colored part, and the support material is indicated in orange colored part. Fine. And we can increase this thing or decrease this thing. Fine. So this is my first layer. My first layer will look this way, because in the machine I have selected that the first part should always be support material. Fine. I have the flexibility of changing this thing. Fine. Now currently in my machine the setting is done in such a way that the first layer will always be model material, support material, sorry. So support material is indicated in orange color. This is the orange color. I'll just gradually increase this one. So this is the layer 2, layer 2, layer 3, layer 4. So from layer 13, layer 2, okay, layer 10 and 12. From layer 11 I can see we have the model material. So this is the green colored portion. So in the real time condition, how the printing will take place, it basically gives us the idea. So likewise we can have, this is the way it will start printing. Fine. So you can see this thing. And talking about this yellow colored portion, we have a light yellow or light green portion. You can see this portion. So this is a seam. Now what is seam? Now when the printing starts, it starts from a initial point and completes the complete path and reaches a final point. So it basically shows us the initial and final point. I can yes, you can so you can see we have a slight green colored portion or a division here. You can see this is the division here. So this indicates the initial point. So the nozzle will move in this direction and it will come and finally reach its final position. So in between we have a light green color portion or a division can be seen here. So this is a seam. Fine. So it basically shows us the starting and end point, this part. Fine. So this is a seam visualization. Now why it is given is that sometimes in a part the seam will come when we finally print the part, this line will continue up to the final layer and will have a straight line or some kind of impression we may have. So currently I don't have any model, so that I can't show you, but basically after printing the whole layer, like suppose now the total layer will be 303 layers. 303 layers is the total layers we have in the model, in our material, in our part, in our geometry. So the seam will continue. Fine. Now you can see the seam has shifted its position. Previously it was in some other position, and we will also find that the seam will have its effect on various locations. So in this part you can see we have a seam here, one more here and one more here. So what happens is that after when we try to print it, we will have some impression on the part. The impression is because of initial and final point. Fine. So this is the part where we can see the we can view the slicing, that is the part by part how the model is being prepared. We can also go for the animation part. So in the animation you can see layer wise it is automatically showing. So you can see here we have a seam, we have a single seam here. This is the light orange color. So it is continuing from 0 layer, it is continuing till so see it is continuing till the last portion, I think. So we'll have a seam here. Fine. So the major seam that is in the central position can be seen up to so this is the seam. It can be it is seen in the major portion of the part, and will have a impression or a straight line in the model. So as to avoid this seam line, we can make some changes in the video. So this is the basic part. Okay, let's move to the other part. Fine. So we have a this is the how do we select the unit we have in so we are not going to change this one. You can say the unit is in we have some options like centimeter, inch, meter. Fine. So we are not going to change it. Now we have this option that is called the material assignment. This is the tray setting. This is called the tray, the entire section. this is the entire section and it is called tray, and this is the perch tower we have here. In the previous video already shown. In the machine we have selected ASA, so we will just change it to, okay, let's keep it ABS. Now it is ABS. Thus in the slice height portion, this is the slice height, we have some thing written here. So what is this? This is the resolution. Fine. So we can in the, for ABS, only for ABS material we have this many resolution. This many resolution means the layer thickness of the, what will be the layer thickness when the nozzle is printing the thermoplastic in the tray. So what will be the thickness, the initial thickness, and throughout the body what will be the thickness. So we have 0.1270 mm, we have this many settings we have here. Fine. So if we keep it lower, our print quality will increase. Fine. So for demo purpose, since we are doing the demo purpose, or this is not a very important part, so we will seek the highest part. Fine. Selecting this, the higher value, the resolution, we are increasing the we are decreasing the resolution here. Fine. Since we are decreasing the resolution here, the print quality will decrease. Fine. If we are choosing a lower value, fine, suppose we are choosing 0.127, then we are decreasing the resolution, sorry, we are improving the quality. Fine, we are decreasing the number, but we are improving the quality. The layer height we are decreasing, and the quality of the part will increase. Fine. But for ASA, if we select here ASA, so let's check for this one, we have this many, same again. But for TPU, talking about TPU, we have a TPU material, we have only two resolution. Fine, that is 0.1778 and 0.2540. so these are the two resolutions we have. But for ASA and ABS we have so many. For PLA we have only one resolution, that is 0.2540. Fine. So since we have in the machine we have ASA, so we will select here ASA and we will select here 0.3302. Fine. So we are increasing this one and the part quality will decrease. Fine. This is the support material, we have only one support, that is QSR, so it is selected here. And this is the support tip. In the previous video I have showed you we have a the head, the nozzle head and the support head. So basically in the for the company which the company are providing us this T14 head. Fine. So they have many models like T12, T13, T15, T16. So for this particular machine we have T14 head, that is support head and print head. This is the model setting. We have a build plate style, we have a, this is the build plate we have here, we can call it tray or build plate. So we'll keep it normal. Fine. And we can't change it. We have a perch part type, we will be putting it full height. This is the perch tower, this is the perch part, so we will keep it full height up to the height of this one. Fine. And we have a system model, we can change it. System model is basically we have see we have this is the part exclamation mark, you can see. So basically if you put here, it will show this what they are saying, like what we have selected here normal. So what does it mean? So we have here model has no feature that require special processing. So we have a simple geometry, so we don't need, so we'll just put it normal. And here we have a first layer material, that is support material. Fine. So whenever if we do this printing, first layer will always be support material. Fine. And the advantage of putting support material is that support material can be easily taken out from this tray. If we put here part material, it will be very difficult for us to remove the part material, because it sticks very rigidly onto the surface of the tray. Fine. So these are the basic settings we have here, and we have how much percentage of material we need here. Fine. So this is the model material, let me select the first one, this is the first one. So it will also simultaneously show you the message. This is showing that this is the sparse setting, best used for further reducing density when structural integrity is not the primary concern. Now this chessboard tool, we are not going to give any twisting force or compressive force or tensile force. Basically we will just make it for playing. We don't have any structural, we don't need any structural integrity or no forces is being induced on the part. So we can select this part. Fine. If you are selecting this one, automatically this one will pop up and it will say us that it is the how much percent of material will this part will have. So the infill density is only 12%. So out of 100%, only 12% is 12% of the material will fill this part, and rest of the part will be void. Fine, we can also increase this one, make it 100%. Fine, but we will not do this one. We'll keep it as per the setting, that is 12%. Fine, we have one more setting, that is the okay, let it come. Okay, we have sparse double dense, best used to reduce overall density while maintaining structural integrity. So you can say here we have a average situation, like we also need to reduce the overall density. We don't need the model to be very much dense, and also we need to maintain the structural integrity. We are having some kind of nominal forces we have in our part, and also we don't want the density to go very much high. We don't want 100%, 50%. So we can select it. After selecting this, you can see automatically infill density becomes 24%, and also again we can change this one. Fine, so let's keep this one. We have this one, let it come. Okay, so basically it's showing that hexagram, best balance between material usage and structural integrity. So the computer, the software will automatically decide that it will create a balance between the structural integrity and also the density. Fine, and finally we have sparse highly dense. So here it will be highly dense. Fine, so in this case the software will automatically decide depending upon the geometry, and you can see in infill density is showing this 0%, and I cannot even change this one. So automatically it will take some value depending on the part which I am painting, depending upon the design which I am giving to the computer. Fine, and here we have 35%, and last we have this solid. It will make 100% solid, and also I can't change this one. Fine, so we have these settings. So since we are making this chessboard piece, so we'll make it in the lowest density. So this is the infill density, basically how much percentage of material is going to fill the part. We have a body thickness, so we can increase this one, decrease this one. Now talking about body thickness, so talking about body thickness, we have here body thickness. Fine, so I'll just show you what is body thickness. Fine, so this is body thickness. Now right now suppose we are making one cylindrical part. This is the cylindrical part we have here. Fine, maybe a test tube kind of thing, cylindrical part, or maybe a bar you can say. Fine, we have a bar here. This is the bar we are going to make it. So talking about body thickness, what is body thickness? First of all, when how does the printing takes place, I will just show you. First of all, whenever we are making any kind of model, first of all you will make the boundary. Fine, so let's say this is a square block or maybe a circular part, anything when it will print, it will be first of all make the boundary. Fine, after making the boundary, it will just try to fill the portion. This is the type, this is the way the nozzle will fill the entire section of the part, and layer wise it will try to increase, gradually it will increase. Fine, so talking about the body thickness, first of all the 3D printer will make the boundary and it will do the infill. This is called the infill, FIL. So infill. Now just now I showed you the infill density. Now if I increase the density too much, that is around 90%, let's say we are making it 90%, we need the structural integrity, we need the part to be very much strong in nature. So what we will do is that since it is 90%, if I'm assigning the software to be 90%, the infill density, it will just try to, it will make a minute part, it will print in such a way. Fine, so very minute location is also, it will try to fill the part with the ABS material or ASA material, the printing material. Fine, if you are giving 5%, suppose this is the 5% infill density, what it will do is that first of all it will make the border, this is the boundary it will make. After that just simply it will print in this way. So if you compare this section and this section, this is 5% and this one is 90%, so you can see the difference. This is called the infill density. Fine, infill density. So how much dense my part will be, it depends on the infill density, how much we are assigning it. Fine. So talking about this one, this is 90%. Talking about this one, we have 5%. Talking about 100%, so it will completely make it, completely it will fill it. Fine. Completely the part will be covered, and this one we can call it 100%. Talking about body thickness, now it is making the boundary first. But what I can do is that, suppose in my part I need compressive force. Now after making this model, I will be testing this part for compression loading. Fine. So for this one, I need to make the boundary very much strong. What I can do is that I can create multiple boundaries here. So this is the first boundary, this one is the second boundary. I'll make one more boundary. This is the third boundary. Let's say make it fourth boundary. We'll make 4 boundary. So this is called body thickness. Fine. So total we have here 4 boundaries or 4 roster. It is also called roster, and after that it will start making the infill in this direction. So it will make the infill. So this is called the body thickness. Fine. One more calculation. Okay, let me also show you the layer thickness. Layer thickness. Now in the software I showed you, whenever I selected ABS and ASA, it gave us something in resolution. Fine. So this is the resolution you can see. So we have 4 number of resolutions here. I'll just write it. Fine. So we have 0.1270 resolution. We have one more resolution, that is 0.1778. we have one more resolution, that is 0.2540. one more resolution, that is 0.3302. so these are the resolution. I told them these are the resolution, RESO. Fine. This is the resolution. But what does it mean? Whenever the printer is printing the first layer or the overall layer, any layer, fine, let's say suppose it is making this layer, this is the first layer it is making. So the thickness, what will be the thickness of this layer? Fine. What will be the thickness of this layer depends on this resolution what we have selected. So basically if we keep it lower, suppose we are selecting this one 0.127, that means our thickness will be 0.127 mm, and by selecting this one we are improving the quality of the printed parts. If suppose we are selecting this resolution, that is 0.3302 mm, that means the thickness will be T here will be 0.3302. Our print quality will decrease because we are increasing the thickness. If you are keeping it lower, that means very minutely it will create the model. Fine. So this is the thickness we have here. One more thing, let's say this one is our 4 mm thick. Fine. We have a thickness of 4 mm in this part. Now if someone tells you that what will be the condition in the 30th layer, so how you will find the any condition, like if there is any design here, let's say we'll make a semicircular part here. So this is a semicircular part in between my 4 mm. So what will happen in 30th layer? So basically I'm showing you the slice here. We have showed you the slicing part. This is the slicing part I've showed you. So what will happen in the slicing part? So this is the slice I showed you, right, in the layered wise position. So how do we calculate the 30th position? Fine. Now if suppose I am selecting this resolution, that is 0.1270. fine. So what I will do is that I will simply divide 4 mm divided by 0.12. Sorry, here I need to know the total layer, how many layers will be formed. I don't know number of layers here. In the software I can see the maximum number of layer is, that is the maximum number of layer is 233 layers we have here. Fine. This is the maximum layer. But if I have this one, the total length of this specimen is 4 mm, how many layers we will have? So what we will do is that 4 mm is the total thickness divided by the resolution, will get the number of layers. So let's check what is the how much value we find it here. So 4 mm divided by 0.1270. So we'll have here 31.49 layers. layers. So even in the software we can find how many layers will form here. In the slicing position we can obviously find by using the slice, we can find the total number of layers, how many layers it will form. Also mathematically we can find, it depends on the resolution. So the importance of resolution is to find the number of layers also. This many number of layers, 31 layers will have in this part. Fine, it depends on the thickness in z direction. So this is the setting we did here. Fine, this is the lowest setting we kept. This is the body thickness. I showed you what is the body thickness, that is the increasing the boundary. So we can make it maximum. If we make it maximum, the body thickness, that is the boundary, will become 5.48 mm. Fine, so let's keep it very less, maybe this much. Okay, fine. And this is the infill angle. So talking about the infill angle, again we have this option. This is the part. So how, in which direction the nozzle head will print it. So we have selected here 45 degrees, so 45, it will be in this direction. Like suppose if we select here 90 degree, then what will happen, the printer will print in this direction, If we select here 180 degree, it will print in this direction. Fine, so basically it is showing us the orientation, in which orientation the nozzle head will print. We have here thick and thin walls. This means that if we have very thin walls, we have anything which we are printing, any kind of wall, the thickness of the wall is 1 mm or 2 mm, so we can use this one. And we use this thing, we use variable with infill. So you can see here what happens is that if we have very small gaps, you can see the message here, fill small gaps in the infill using a variable with breadth of model material. So if in case in the model, in this material, we don't have any small voids or small gaps, if we have any very small gaps, the model material will try to fill this part. Fine, and we have this support angle. The support angle is smart. Use model material. We don't want to use model material because model material is very rigid. Fine, we have here growth support. We have only small only because in this part we don't find some such support, because it is sitting onto the over the platform, so we don't have any support here. Fine, self-supporting angle is 50 degree, that we don't need here. We have some other options like stabilizer, we don't require here, and anchor and all. Anchor is basically if we want to do the anchor here. So this is the anchor basically means when we feel that our part will fall while printing. Like if suppose we take one assumption that if the base of this chess tool is very much small, maybe 2 mm or 3 mm, this much in diameter, so while printing it might fall. So because we can use here anchor means to hold the part. Fine, so if you select here, so you can see there is one anchor, that means it will try to hold this part. Fine, and we can also increase the diameter of this part. Fine, so you can see this is the diameter we have here, so we'll just reduce it. Okay, so it has reduced. Talking about the orientation, so let's change the view first of all. So talking about the optimization, so the software has some optimization tool. So if you simply click it and make this, arrange this tray, so it will do the optimization might be of time optimization. Fine, so it is automatically placed in some location where the optimization is done. Fine, and we have this orientation. Fine, so this is the orientation how we do. Fine, now since the print will start from this direction and it will continue till the top position. So what we can do is that to reduce the time, if you see the time now, let's do the time estimation now. So it is showing us that it will take 1 hour and 22 minutes to print this part. Fine, we'll do the optimization, some more optimization we'll do. So we'll make in this position. Fine, and we'll check for the estimation. So it is taking 1 hour and 7 minutes. Fine, previously it was 1 hour and 22 minutes. So here what happens is that since the printing starts from the base and it gradually moves in the Z direction. Now we have reduced the Z direction. Now the printing part is lying in this direction, in X direction. Fine. So we have reduced the height. Since the height is reduced, the printer will reach this much distance. Fine. So in this way we can do the optimization and reduce the time. Fine. And we have some orientation to the face. So let's select this one, and if we want this position to be in the bottom direction, left direction, right direction, we can choose it. So let's do select this face. Okay, this is the front view. We have select this face. Now it is giving us this option how to orient this plane. Let's say we give it bottom. So let's see what happens after giving the bottom. So you can see the head part came in this in the downward position. Fine. And the base got uplifted, so it is making it upside down. Fine. So this is the part, this is the how we can do the orientation. Fine. So let's make it in this direction. So you can see the head of the chest tool went in the downward position. So this way we can do the orientation face to the plane depending on the in which direction we are going to do. Let's say we are going to do this one. So we have left right option, front option, back option. Fine. And we have here scale. Like suppose we want to reduce the overall thing, we want to in the X, Y and Z direction we want to reduce it. So we have here uniform scaling. So we'll just reduce this one to, let's say, 50%. So the entire section will decrease. Fine. Let's make it 100%. Okay. Fine. Now if I change this one, we don't want uniformly to decrease or increase the thing. So now we can individually we can decrease. Now in the, if I change here, if I make it 50% here, only the X direction will change. Fine. So let's change the Z direction. Let's make it 20%. So you can see making this one 20%, this one the Z direction reduced, but the X direction and Y direction are same. Fine. Because we have unticked the uniform scaling. So let's make it 100. So everything 100 mm. Fine. So these are the things we have here, basic things of the software. Fine. So that's all we have here. Now what we will do is that we will just go to file, and here we have the export CMB file. So CMB is the extension required for the required by the machine to print this one. So we'll do the export, and we have the pen drive here. Fine. So we'll just name it, we'll give it ME354. Fine. This is the CMB file we have here. This is the file extension required for the machine, and we'll just save it. And here we have the option for including the purge tower. So it is saying for the purge tower. Fine. So exclude purge tower part from CMB. We want to include it. Purge tower increases our print quality. So it is showing us the export preparation of export. Fine. It has successfully exported. Fine. We have the pen drive here. So we'll take the pen drive out. So this is the machine we have here. So first of all, in the machine we'll have this type of message: is the tray ready for another job, yes or no? Right now we don't have any platform inside. You can see the metallic part. This is the metallic part we have here. So we'll take one tray. This is the tray we have here. We can call it tray or platform or anything. Fine. So we'll open this one, place it. We have these are the slots we have here, and we have these are the parts. It will go inside the slots. So we'll put it here. Fine. Okay, fine. So it is fixed now. Now we'll close the door. Fine. Now again it is showing us the message: is the tray ready for another job? Yes, it is ready. And here we have the model and support. So you can see right now the temperature 70 degree, in both the conditions 70 degrees Celsius, and we have the ASA material that is 63%, and QSR material, that is the support material, we have 32%. Fine. So we'll just put this pen drive here. and we have this plus symbol. We'll press it here. Since we have inserted the USB, so we have things in the USB. Also in the internal storage we have some of the things. These things are given by the company. Fine. So you can see these are the .cmb files. Fine. So these are the files we can have here. Also they have written here text organizer ABS, so we can use only ABS here. PLA, they have mentioned PLA here. Fine. And also TPU, so we don't need these things. So we'll just move to USB part. So here you can see this option. We have this load file option, so click here, and we have this USB option and internal storage option. So we'll move to USB option, and here we have the file. So you can see this is ME354 CMB file. So we'll click here and we'll do add to queue. So it is copied now. We can take the pen drive out now, and we'll just go for the printing. So in the screen you can see these options we have here. So this is the file name, this is the time. We can see that is 1 hour and 6 minutes. We have this QRS material and ASA material, and QSR is the support material. Fine. So these are the options we can view, and also you can view the part, and also you can zoom it. Fine. So this is the part we are printing. Fine. And also you can see the other options like how much amount of material is required for printing this one. So for ASA it is 0.9 cubic inch, and for support material, that is QSR, it is 0.5 cubic inch. Fine. And the size is 98. So this is the total size, and this is the slice height and all. Fine. So we'll just click here print, and it is telling me to place it somewhere in the platform. So I'll just place it somewhere near to the nozzle and the printing the nozzle, both the nozzles. Fine. So both the nozzles are placed in this part, that is the back side of the print the platform. So we'll just place it here, so that the travel time of the nozzle for the part material and support material does not increase. So if I put this one somewhere here, so right now currently our nozzle head is at this position, so continuously it has to travel in this position, again go for cleaning, make the parts tower, come again here. So as to reduce the time, the travel time of the nozzle, we'll just place it somewhere here and go for printing. Fine. So it will start printing now. So in the this home page we have this preparation option. So it is telling us that it is preparing the print. So we'll wait for some time. After that it will go for stabilizing and then some other things, and then it will finally start the print. Fine. So you can see now it is heating. So I'll just show you. Okay, we have the heating option here. So right now the temperature, it is increasing the temperature for both the heads, that is the printing head that in the support head. Fine. So also you can see the temperature is increasing now. It is presently previously it was 70 degree, now it is 71, 72 something, and it will gradually increase. And also you can see the platform has moved in the upward direction. So this is the platform right now in this position. Fine. And right now the nozzle head will try to purge some material out, some unwanted material. It will purge it out, and then it will try to print the part. So you can see the printing has started, and it has also printed. It is printing the first layer. You can see also see the time, that is 1 hour and 5 minutes, and this is the first layer. Fine. So this is the condition we have here. And also in the inside the machine you can see the nozzles are moving. Fine. So you can see the nozzles are moving here, and it is printing the first layer. So gradually it will print layer by layer, and it will complete the whole part. Fine. So this is how the printing takes place. The printing, so the chess piece which was given, which was designed and given for printing. So here we have the print, you can see. So simply what we will do is that we will just take open this door, fine, and you can say this is the printed part we have here, the chessboard piece, and this is the lever via which we can release this platform. So we'll push it down this way and then simply take it out. So you can see this is the part we have printed, but also we have the support section. You can see these are the supports we have here, fine. This is the support we have here. The entire section is covered with support, fine, and this is the actual part, and this is the perch tower. So I told you what is perch tower, and this is the ASA material, and QSR is the support. So what we will do is that we'll just give a twist here, fine, in this way, so that it simply comes out. So this is the way it comes out, and you can say these are the support we have here. So this much layer of support is required, and even here we have some integrated shapes here. Some complex shape was given in the head. So also in the head you can see it is almost 80% covered with support material, so as to give the support to the complex parts, fine. So this is the part we have, and this is the perch tower. We'll simply take it out and throw it, fine. And now we will take this and put it in the tank. So we have a tank in our institute, so as to remove the support materials, fine. So I'll just show you how the tank operates. We have some solution there. So in the tank we will just drop this part and wait for some time. We'll select some temperature, we'll heat the tank. The tank is filled with 40 liters of water, and the water is mixed with some soap, fine. So those soap along with water, and we'll just heat it up to 70 to 80 degrees centigrade, and drop this and put it for around 3 to 4 hours depending on the shape. So since it's a simple shape and very small in size, so the time required is very less. If we have a very complex shape, I will just show you. We have one complex shape there, so it took around 2 to 3 days to remove the support, fine. So now we'll just move to the tank and see how does we remove the support part. So this is the tank we have here, fine, and it is filled with 40 liters of water, so you can see. So the water is mixed with some kind of soaps and all, some kind of chemical solution we have given here, and we will just simply dip it here, fine. We'll just place it here, close the lid, close this section. And right now we have some current issues, like we have in the campus we don't have electricity, and it is running in UPS connection. So we don't have UPS connection in this power socket. This is not the domestic line, so right now I can't operate this. So you can see, I'll just simply show you. So this is the power button. We simply will on the power button, and it will show the heater is off or on. So if we switch it on, the heater will be on, and here 50, 60, 70 and 85 are the temperatures, which temperature I need, because we have 4 different materials, that is ABS, ASA, TPU and PLA. So for those we have different temperature ranges. So we will simply keep it around 70 to 85 in between for ABS and ASA, simply this one. For PLA we don't have any extra support for PLA. If we print this one in PLA, so the PLA itself will give him support, fine. So no other support is required for PLA. Just in case of ABS and ASA we have QSR as the support, but for PLA itself is the support. So for PLA we don't need to use this one. For TPU we have the support system, fine, and we will use this one for dissolving as well as for ABS and ASA. So these are the temperature ranges we have here. This is the power button, this is the set temperature. Now if the temperature we can how much this time is we need for this one. Like suppose we have a very simple geometry, so we think that we will give around 3 hours or 4 hours time. So we will just increase this one or decrease this one and set the time, so it will show us the time here, fine. So this set is for time, this is the power button, this is the heater on or off, this is the status it will show us, and these are the temperature ranges. So after this we will, after the cleaning is done, we'll take the sample and use it as per our necessity. So this is this tank where the support is dissolved, fine. So thank you, that's all.